this problem. For this problem, it almost says that our best approximation ever matches the best algorithm. And for many problems, the best upper or lower bound that the unique gains conjecture gives are considerably better than the bound that we can obtain using standard assumptions.
Yeah, okay, so we will proceed.
Okay, so how much time do I have?
No, at least at five minutes plus the over penalty for the coffee, illegal coffee drinking.
No, 15 is okay, Yura. 15 is okay.
Depends. So I can either answer any questions about this. I can describe some different, say a little bit about some different program, what it is, or I can say a couple of words about other applications of some different programs. So what would be better?
I prefer to listen about unique games.
Yeah, maybe you can explain what's unique games.
Because I heard so much about them and have never understood why we need them.
But I will be able to prove any Huggins result.
Okay.
So the unique gains conjecture is the following. We have a graph G, and we have say k different labels or colors, and our goal is to color our graph with these k colors. But for every edge of the graph, we have a constraint. So for every edge UV, we have a permutation pi UV on the set of colors. Pi UV is a permutation of the colors. And our constraint is that pi UV of XU, where XU is the color of the vertex U, should be equal to XV, to the color of V. And our goal is to find a coloring that maximizes the number of satisfied constraints. So this is the unique gains problem.
Why it is called so?
It's called so because it is similar to two-prover verifier gains, and he making that you are a prover, and you are a verifier, and you ask two provers for colors of these two colors. They give you two colors, and they cannot talk with each other, and then you compare that indeed pi UV of this color is equal to V. So originally this problem was motivated by such games, and therefore it's called a game, and it's called unique because every constraint is a permutation. So the color of one vertex is uniquely determined by the color of the other vertex.
Excuse me, maybe I'm missing something, but it seems like the color of all other vertices is determined by the color of just one vertex.
Oh, if you want to satisfy all constraints, then, but the idea is to maximize the number.
You want to maximize. Typically, you cannot color to satisfy all constraints.
So yeah, that's true. If in the optimal solution all constraints are satisfied, then it's very easy to satisfy all of them.
Is the graph directed or not?
In a sense, for every permutation we have a direction which you need applied.
So for in other direction, of course, you have
so for each edge you have two permutations actually.
Two inverse permutations.
You have PUV and also PVU, which are inverse. Which is inverse. Okay.
Inverse?
Or maybe it's not a permutation, but just correspondence between U and V.
Okay. Yeah. But I didn't understand really what is the game, who plays and what is the goal of the players.
It's not a game anymore. It was motivated by games, and not games in the game theoretical sense.
Games, well, when two provers and verifier.
Yeah.
So I play against you. I ask one of you the color of this vertex. I ask one of you the color of this vertex, and you cannot talk with each other. You give me these colors, and you win if actually pi v of xu is equal to xv, and I win if this is not true.
Yeah.
So what does the conjecture state?
Okay, so this is the unique games problem. Now the unique games conjecture says that for every epsilon there exists delta, and such that for every game and the game such that and some threshold number of colors, it's empty hard to distinguish unique games with k colors in which either 1 minus, so these two instances, in the first case we have 1 minus epsilon fraction of all constraints is satisfiable. In the second, only delta fraction of all constraints is satisfiable.
Then inequalities, at least 1 minus epsilon,
At least,
most.
yeah. That's right.
But this is strange, then probably you should...
So it's like a promise problem.
The date is less than 1 minus x.
No, probably you should say for each... The bigger is epsilon, the more difficult is this, yeah?
No, if epsilon is small.
The smaller is epsilon, the smaller delta is.
So we have a 1 minus epsilon, and we should distinguish between 1 minus epsilon and delta.
The smaller epsilon.
So we have just interval between 0 and 1, and here we have epsilon size, delta size, and then epsilon size.
Yes.
So the smaller is epsilon, then easier is
Yeah.
to distinguish.
Right, yeah. But this says that even if epsilon and delta are very small, oh, actually, sorry.
It's very strange, the quantifiers
Sorry,
are...
I'm sorry about this. Yeah, sorry.
Well.
Yeah.
Okay.
So and what can be proved for this? For example, if for some epsilon and delta, or even without any hole between them, is it NP hard or what is known?
No, it's not known. This for some epsilon and delta that two are both are very small. For
No, but just say it's greater than 1/2 and less than 1/2. Then it's NP hard to distinguish or not?
Do we need 1 minus epsilon be more than delta? Be greater than delta?
So it seems that we want, even if we have a promise to have a gap, then it's difficult. But imagine we don't have any promise for a gap, just more than 1/2 and less than 1/2. It should be the most difficult version of this.
We can't say. We don't know anything.
которых меньше, чем ты, это же разные, даже если эти два отрезка пересекаются, все равно класс будет разный.
So it's quite possible, for example, that this is in P, for example.
No, okay. It's not that it's not. Okay, not this. You can't. Okay.
What happens if it is not in P hard, but it is in P? What happens to the world? Well, we are unable to prove that it's in P hard. Yes.
Yeah.
What happens if it is polynomial time solvable? What happens to the world? We can.
There are no.
Everything in Max's and P, everything has a polynomial approximation scheme, or what?
No, there are no implications.
No implications.
No, there are no implications on the polynomial hierarchy. No applications at all.
Okay. If it's false, that there are no implications, and if it's true,
then now there are a lot of lower bounds on approximation that are true only as unit gains conjecture. So, for example, this algorithm of Bowman and Williamson is optimal.
Okay. Does this mean if there are implications only in one direction? Does it mean that actually the unique games problem is hard for some class of problems under certain reductions? It is hard but not complete for, say, for Max's and P, or because if you have reductions from, it seems like you
so far most reductions are from the one-way reductions. So there are a lot of reductions to unique gains problem, but there are no reductions from unique gains problems rather almost no reductions in the other direction.
From unique.
So
okay, which direction do we have?
We have the reduction to unique gains.
So if you have a good algorithm for some other problem, then we can solve unique gains.
Right. If we can solve max card better than the Gorman-Williamson.
So it's a kind of a complete problem, but for reductions, for a reverse category where you have reductions in the other directions. So it can be reduced to everything else, but we can't say that everything else can be reduced to it, correct?
Yeah.
Yes?
if what you say has some meaning, that's probably correct. Just what you said. Yeah.
It's like a somewhat unusual phenomenon.
Actually, it's a very interesting question to study unique games complete problems, and now many people are working on it. And many people are trying to find reductions in the opposite direction, but it's not easy. So, for example, it would be a great result to show that the reduction from unique games to max cut. That if you can solve unique games, then you can solve max cut. Any questions?
So the question is, what gives semi-definite programming for unique games?
So there are several algorithms. So one of them, roughly, so you can satisfy, if in the optimal solution 1 minus epsilon fraction of all constraints is satisfiable, you can roughly satisfy this fraction of all constraints.
You do not write like this. So what's the promise and what's the performance?
Promise is 1 minus epsilon, and this is what the algorithm can do. 1 minus square root epsilon.
Yury, and the first line is k to the something.
K to the power of minus epsilon over 2.
Okay.
Epsilon square root log n. log T. And here,
So the first is very weak, as I understand.
but it's better than a random assignment. And actually, if you improve constants here in this big omega notation or in big O notation, then you will disprove the Unigame's conjecture. So these two results are optimal assuming the Unigame's conjecture. So,
And all of them are by semi-definite programming?
yes.
Oh.
And the last one also using metric embeddings, the topic I talked during my first lecture. So it's a combination of semi-definite programming and metric embeddings.
So people believe in Unix game conjecture.
Some people believe.
Some people, well, almost everybody.
No,
No.
some people.
There exists some fraction of people who believe and some who disbelieve, and other stupid people do not know about this, so they have no opinion. Yeah.
We can ask Yury, does he, if he believes. You believe?
No, it's a very personal question. You shouldn't ask about belief.
Well, I wouldn't say that it's NPH.
Like asking if
It doesn't make any
he
sense
believes in God.
to say that it's NPH. I mean, we don't have any reason to believe that it is NPH, but I would be surprised if there is a polynomial time algorithm.
Yeah, you kind of weak belief.
I believe in a big form of it.
Yeah.
And also, from what you said, it follows that you believe that NP is different from P, right?
Different from NP?
Yeah.
Yeah.
I have deduced it.
You don't believe
Mm.
By pure logic, no.
Yeah. Exactly. Okay, so I have to say that usually people who go to the United States often complain that they have a very boring task of teaching a stupid undergraduate student. But now we see that it's not probably very boring, but also useful, because compared to your previous talk before you went to the United States, it's much more clear. We understood a lot more than usually. So it's a good training for. Okay, so. Yeah, now it's legal coffee break.
Your last speech was politically incorrect.
В чем была разница?
Ну, ты сказал, что Stupid American student.
Многие люди, которые жалуются, ты говоришь, учить буквы, мне кажется, студент. Нет, потому что люди жалуются, значит...